Chapter 6, Section 1, Estimating with Finite Sums. That's the textbook's title. We're going to call this Riemann sums. Riemann sums. That's what they mean in the textbook when they say estimating with finite sums. They're called Riemann sums. Number 6 on page 274. That's where we are, page 274, exercise 6. Refer to the region R enclosed between the graph of y equals 2x minus x squared and the x-axis for x between 0 and 2. The graph of y equals 2x minus x squared is a parabola. It passes through the point 0, 0. When x is 0, y is 0. There's a turning point. Turns down, crosses the x-axis at 0 and at 2. We are going to partition this region, 0 to 2, into 4 subintervals and show 4 rectangles. So what does all that mean? First of all, we get started with this formula to memorize. Delta x equals b minus a over n. We'll see this a lot. Get familiar with delta x equals b minus a over n. B is the end of this interval. A is the beginning. And n is in the question. It says 4 subintervals. N is the number of subintervals. It's also going to be a number of rectangles. So know this formula by heart. In this exercise, delta x is 2 minus 0 over 4. These numbers are a and b, given interval. 4 is given, number of intervals. So delta x equals 1/2. We're going to use decimal, 0.5. This is how we get it. Then we create a table of values where the x will be starting at 0. It's given. Change x by what we just calculated. Delta x is 0.5. So the next x we get by adding delta x. Add delta x again. Add delta x again. Add delta x again. And this is where we would stop because the interval is 0 to 2. The y column is y is 2x minus x squared. So I'm going to put all of this in my calculator. When x is 0, y is 0. When x is 0.5, y is 0.75. When x is 1, y is 1. When x is 1.5, y is 0.75. And when x is 2, y is 0. We're going to plot all these points, which actually create the parabola that we just saw on the previous page. But I just want these points, not connect them. The point 0, 0, 0.5, 0.75, 1, 1, 1.5, 0.75, and 2, 0. Do not connect the dots. For each of these intervals, from 0 to 0.5, and from 0.5 to 1, and from 1 to 1.5, for each of these, and one more, from 1.5 to 2, for each of these subintervals, I'm going to ask myself the question, which number is on the right? So the first interval is 0 to 0.5, 0 to 0.5. I say, which of those is on the right? Since 0.5 is From there, I go to the plotted point on the function and make this the top, this flat, the top of a rectangle. The next interval is 0.5 to 1. Which of those is on the right, 0.5 or 1? Since 1 is on the right, I go to the point that's plotted when x is 1 and make this the top of a rectangle, flat top. 1 to 1.5, which is on the right, 1.5. From 1.5, go to the y coordinate, the point that's plotted, make this flat thing the top of a rectangle. And there's one more interval, 1.5 to 2. Which of those is on the right? 2 is on the right. So the last when x is 2, y is 0, so the height of the last rectangle is actually 0. There are 4 rectangles here. They're called right rectangles, RR. And it looks like there's only 3, but that's because the 4th one has height 0. Because when x is 2, y is 0 in this function. So we are going to find the areas of these 4 rectangles, even though one of them is kind of invisible. We're going to find the areas of those 4 rectangles and add them together. The result will be an approximation. The result, when adding the areas of these, will be an approximation for the area between the curve y equals 2x minus x squared and the x-axis from x equals 0 to x equals 2. We're going to say this area that I just described here is approximately, using a right rectangle approximation method. That just means the areas of these 4 rectangles. Since we used 4 rectangles, we ordinarily put a 4 subscript here, indicating that we found the areas of 4 rectangles. Every one of these rectangles has a width of 0.5. So that delta x equals b minus a over n, that is the width of each rectangle right here. Each of these rectangles is 0.5 wide. So we take the width of the first rectangle times how tall it is, which would come from this table right here. It's actually in the picture, but it's 0.75. And we're going to add the area of the next rectangle, which has 0.5 width. The second rectangle is, the height is 1. The third rectangle has 0.5 width. Third rectangle, and it's how tall? It's 0.75. And the last rectangle is 0.5 is the width, and it's 0 height. Point 0.5 times 0.75 plus 0.5 times 1 plus 0.5 times 0.75 plus 0.5 times 0 is 1.25. That is the answer called the right rectangle approximation method. Subscript 4, meaning the areas of 4 rectangles added up together. That number, 1.25, is an approximation for the area of the region between this curve and the x-axis. We're going to say the area of this region is approximately whatever number we just got. I forgot what it is. 1.25 square units. Of course, it's not exactly that, because we added rectangles. So that's it. 1.25 is the right rectangle approximation method. It also says to find the midpoint approximation method. So continuing exercise 6, the midpoint rectangle approximation method, still using 4 rectangles because that's what it says in the directions. This time for each interval, there's still 4 intervals, so we still would use the same delta x. This is b minus a over n, that's n. Same interval, 0 to 2. But this time for each interval, where the first interval starts at 0, because that's where we're supposed to start, and goes to 0.5, because that's the change in x, or the width. But this time I say, in this interval, what x is it exactly in the middle? Since that's 0.25, we need to know what y is when x is 0.25. And then the next interval is from 0.5 to 1. What number is exactly between 0.5 and 1? That would be 0.75. The next interval is from 1 to 1.5. What number is exactly between 1 and 1.5? That would be 1.25. So the x's are all the exact middle of each of these intervals. The same intervals as the first part, the R ram. The last interval is from 1.5 to 2. What number is exactly the middle between 1.5 and 2? That would be 1.75. By the way, you get these numbers by adding the endpoints of each subinterval and dividing by 2. Add 1.5 and 2 and divide by 2. That's how we get these x's. The y's are from y equals 2x minus x squared. So, using y equals 2x minus x squared, when x is 0.25, y is 0.4375. And x is 0.75, y is 0.9375. And x is 1.25, y is 0.9375 again. Parabola, it's that symmetry. When x is 1.75, y is 0.4375. Here's the thought process. We'll say, in this interval, 0 to 0.5, what's the exact middle? And then whatever x is there, go to the corresponding y from our table. Let's say it's there. Make this point where I'm plotting right here the top of the first rectangle. These are all rectangles. Between 0.5 and 1, the y coordinate exactly in the middle, for the x that's exactly in the middle, is up here somewhere. This point here, this y value makes the top of the second rectangle. These are all called midpoint rectangles, MR. Between 1 and 1.5, we find the x, and then the corresponding y. And then the last interval, find the exact middle, find the y coordinate, write those. So these 4 rectangles are called the midpoint rectangles. We're going to use the middle of each interval to get to the y value. Or when I say get to the y value, I mean the height of these rectangles. The midpoint rectangle approximation just means the areas of these 4 rectangles all added together. All of these rectangles have the same width, right here. So instead of writing it every time, I'm going to factor that out. The area of a rectangle is how wide times how tall. These numbers are how tall the rectangles are. The first rectangle is this tall, 0.4375. The second rectangle, here's the height of it, 0.9375. The third rectangle, this is the height over here, 0.9375. And the last rectangle has this height, 0.4375. The area of a rectangle is the width times the height. They all have the same width. So I factored that out of all of those. .5 times 0.4375 plus 0.9375 plus 0.9375 plus 0.4375 is 1.375. 1.375. That's called the midpoint rectangle approximation method using 1, 2, 3, 4 rectangles. That number, 1.375, is also an approximation for this green area right here, the area between the curved parabola and the x-axis from 0 to 2. So two answers. They're both approximating this area. One is called the right rectangle approximation method. That was, I forgot what it was. Oh, 1.25. And then we have the midpoint rectangle approximation method, 1.375. Okay. Sounds good.